electrophilic aromatic substitution as being a reaction that benzene actually undergoes. Okay? In other words, it basically reacts with an electrophile, but unlike alkenes, it doesn't lose the double bond in the end. The double bond is regenerated because you have effectively aromatic stabilization energy. So that's basically the driving force to get electrophilic aromatic substitution reaction versus addition reaction. And that's critical in the market. So that was kind of pretty easy, right? Because you have to learn some reagents, you memorize some of those. But then I said, you know, sometimes or mostly you have benzene derivatives. And benzene derivatives are those which have this sort of substituent. And of course, in this case, I'm only giving you a benzene derivative with one substituent. A more complicated example is where you've got multiple substituents. And in any of these, you have to ask yourself the question that should it undergo electrophilic aromatic substitution reaction, you will need to consider how fast the reaction is going to be and where is it going to react. And these are the issues associated with this. Because, you know, it's well and good to say that something is going to react. It's not very reactive, okay? And if it's not very reactive, it could turn out to be that it would seem to you that there is no reaction because you don't do it long enough. Let's say you carry out a reaction with NO2, A is NO2, nitrobenzene, you react it with bromine, okay? You leave it for 1 week, okay? You will see that the reaction basically doesn't go. But maybe if you left it sitting for 1 year, the reaction would have given you some product of the reaction. So when we talk about issues of reactivity, it is a relative term, okay? In other words, you're talking about time frame, a reasonable time frame for reactivity. In this case, what we're saying is that we're saying we are comparing it relative to benzene. We say, let's say benzene reacts, you know, within 24 hours. Is something going to react faster, or whether it's going to react slower? And in the case of benzene, because if you think about the fact that benzene doesn't have any of these, it's symmetrical, it can react and the new substituent can come in, or the electrophile can come in and react anywhere, it doesn't really matter. But if you have a substituent here, it can be either the ortho position, which is this guy and this guy, symmetrical down here. This is the matter position, and this is the para position. So there are 2 ortho positions, there are 2 matter positions, and 1 para position. Okay. And this thing here summarizes essentially the substituent effect on aromatic rings. And here we talked about groups that are strongly electron donating, these guys over here. They are donating via resonance effect, very strong resonance effect, donating electrons via resonance, which means using essentially the pi electrons. Although they are a little bit electron withdrawing via inductive meaning that you have a heteroatom which is greedy and it's just going to leave the electrons closer to it than it is to the other partner in a sigma bond, okay? So although you have a minus I effect for all of these, the plus R effect is very strong. Then we have the alkyls, which is including the alkyls and another benzene substituent. These are groups that basically are very strong plus I groups, okay? Especially the alkyl groups are plus I groups. And consequently, these groups here don't have, although they do not actually have resonance effects, they can donate electrons by inductive effect. And therefore they are in total going to react faster than benzene. Because in essence, the ring is more electron rich. They're more electron rich, okay? And the reactivity is such also that you will see that at all of these, they are ortho and para directors, okay? In other words, the reaction will occur at the ortho and the para position for reasons that you've already seen, which I will just summarize in a little bit, okay? And then the other thing is that these guys, which are electron withdrawing groups, They are withdrawing essentially by minus I through inductive, and also electron withdrawing by minus R, which is through resonance, is sucking electrons away from the benzene ring. They are effectively not going to be very reactive, because the overall effect of having electron density withdrawn from the benzene is to make the benzene ring less electron rich. So it's going to react slower, okay? And it is going to react specifically at the matter position. So if you don't remember all of these, just remember all of these guys are matter directing and very slow. All of these guys are auto and para directing. These groups are faster than benzene. This one is a special class which I'm going to describe in a little while. Okay. And this is basically a very important slide as I outlined. I've also shown you these guys over here, but I'm going to just go through one example and draw it out because I didn't draw it out yet. Okay? So I'm going to draw this out essentially for these systems over here, which is essentially having an electron withdrawing substituent. Okay? So I'm going to go to the visualizer and I'm going to work this out with you so that you will know how this is going to work. In this case here, I'm just demonstrating this, and of course, you clearly can do this with quite a number of different groups here. Okay? And I'm saying, let's say, I'm going to use a different example to what I have essentially on the slides over here, just to make it, to give you more examples. I'm going to use the example of nitrobenzene. Okay? Nitrobenzene. And if you look at nitrobenzene and if you drew the resonance forms associated with nitrobenzene, then it's going to look like that. Okay, while I draw it, you can also start drawing the resonance forms and see whether you get similar ones. You get these resonance forms. If you get these resonance forms, you can say that the resonance hybrid is going to be roughly, okay, that's how you've got this circle, okay? But here you're going to have a delta plus, and a delta plus. In other words, you can say for something like the nitro group, the carbons which are auto and para are going to be electropositive. This means that when you carry out an electrophilic aromatic substitution reaction, you know that those positions are not going to be favored at all, because they're not going to be even attracted. So by default, the only positions that are left is essentially the matter position. It's not because the matter position is activated, it's just that the other positions are deactivated. This is critical for you to realize that there is a difference. Okay? It's like, you know, you are trapped on this island, okay, and there's only one guy left, in this island. And you are going to marry this guy, not because he's good looking or he's rich, but just because he's the only guy in the island, okay? So it's not that there is a pull factor, okay, it's just that it is the best of the choices that's available, because the other positions are disfavored. So it's not that the matter is favored, it's just that the other positions are disfavored. So this explains the reactivity of the nitrobenzenes, okay? Because you can see through resonance effect, it withdraws electron so that the system is now going to be electron poor. But NO2 is also a withdrawing group by inductive, so it's also a minus I group. But a minus I group really only affects the carbons which are closest to it, okay? So effectively, although the ring is poorer or is less electron rich, but the effect of resonance is usually greater than the effect of inductive effect. Okay? So in this case, both of these is going to add towards contributing to the fact that the reactivity of nitrobenzenes is less than that of basically that of benzene itself. Okay. 1 point. So now, how do you explain the observed regioselectivity? One way is that you say that it is because of the fact that you look at these positions, they are not going to be favored at, there's no attraction between the carbons on the ortho and the para position, so it basically has to react at the meta. And to demonstrate this, you are going to be able to draw, okay, resonance forms that are, okay, I'm going to just draw the mechanism. So if you react with an electrophile, if it reacts at a meta position, you're going to end up with the structure. Because this is reacting at the meta, so the E is here, and the hydrogen is here, this double bond, this carbon is, this is going to have a plus charge. Then you draw the resonance forms for this. And you get that. You can say that this is what happens when you have a meta attack. So as an example, you can also do an ortho attack. And when you look at an ortho attack, you will see the following. Draw the resonance forms. And we can draw another resonance form for this. But this resonance form is a very important one. If you have an ortho attack, the plus charge is basically attached on a carbon which is next to a nitro group. A nitro group is not going to be, is electron withdrawing, so it's going to suck electrons away, although that carbon is already positive. So this is a destabilized situation, which is essentially what I was describing, okay, that in essence, this is why the meta actually attack is going to be favored, is because there's no actually pull factors, it's just that in this other cases where you get the ortho and the para attack, there are destabilized intermediates or resonance structures. And these are the things that you will need to draw, okay? You will need to draw this if you were asked a question to explain. And your explanation on reactivity is going to be based on what I showed over here at the top, okay? Talking about how either the benzene ring now is less or more electron rich due to the resonance structures. To explain the regioselectivity, you will say there are two instances. If you look at the resonance hybrid, you can see that it is attracted to the carbon, in this case, which is not delta positive, which is basically carbon, the meta carbon. And the second thing you need to show is that you need to show the difference in the resonance structures, basically in a meta attack, and either one of the ortho or the para. You may not have time to draw both of them. They are the same anyway, in a sense. You will get a similar sort of carbon intermediate. Two things, okay? And both of them needs to be addressed in answering a question that is like this. So now if we go back and look at the last bit, which is essentially that on section 43, slide 43, which looks at the effect of the halogen. They are really weird, okay? So if you've got a halogen, you have this very, very strange thing. And the very strange thing is when you have a halogen, this is going to, when X is equal to chlorine, bromine, and iodine, it is said that this is going to react slower than benzene, and then it is going to react at the auto and the para position. This always puzzles people because it's almost kind of counterintuitive, okay? And the best way to explain this is very simply said that when you have an halogen, you have a minus I effect because they are very strongly electron withdrawing virus inductive, okay? And it is also donating effect, but this is actually quite weak, okay? The overall effect is the minus I is going to be stronger than the plus R effect. The ring system is actually going to be overall less electron rich than benzene, which is why it reacts slightly slower than benzene. Okay? It's because the inductive effect outweighs essentially the resonance effect. And therefore, it reacts slower than benzene. But nevertheless, if it reacts slower than benzene and there is still some donating effect, you will see that if it is going to react, it will react at the auto and para position. Because now if you drew, let's just draw one example here. Okay, let's say a bromine, and it reacts essentially at the auto position. You will get the carbocation intermediate over here. Okay, which is destabilized by the positive charge, but is stabilized also by the fact that it can donate electrons by resonance. Okay, and that's basically the logic associated with having it reacting at the auto and the para position, because you will get a carbocation where it is going to be next to the halogen, which is going to be able to give electrons essentially to neutralize the positive charge. And you could say it's not really very logical because I just told you that it is an electron withdrawing group by inductive effect, and that effect is indeed going to be stronger. Okay? But there are two issues here. Okay? The issues is that when you have a minus I effect, which is very, very strong, you're talking about the electron density of the ring system. Okay? The benzene ring system. So in general, you're saying, okay, it is in fact going to be less electron rich. Net total is basically less electron rich. Net total is less electron rich, okay, and if you look at the reactivity, it's not that slower, not that much slower than in the case of benzene. So that's the first question. How fast is it going to run in this race with benzene? It's going to be able to run a little less fast because it's a little bit less electron rich. And so then the next question is that if you are reacting, where does it react? After all, you're now not talking about the reactivity of the system, you're talking about where is it going to react? Of all the positions, which is the best position for it? And the best position is going to be one where there is even a small chance, okay, of being stabilized, okay, which is an auto and para position. It's a very weird situation with the halogens, okay? And the only thing that I can say that it is really, I guess it's a balance of the factors, okay? And overall, the observations is as I've outlined in that summary slide that I have given there. So if we now move back to the slides on the computer, this essentially gives you this information over here. Okay. Overall, the ring is less electron rich, but the auto and the para positions are sort of, if you compare, you know, make the best out of the worst situation. then the alter and the para positions can be stabilized by resonance. And that's basically how this explains the observations which is effectively outlined over here, which was basically taken, this one I know was taken from the Murray textbook, essentially, okay, which is the summary of this. Okay, this then leads me to just end up here with an example. Okay, and the example is shown over here. And this is to give you an idea of why the sort of things that you're learning now is kind of important. And this is the synthesis of diazepam, which is shown over here. With the knowledge that you have actually gained, you can actually work out every single step of this reaction. And isn't that amazing? And you should go and work it out, okay? Draw the mechanisms of each of these single steps, because you will know how to do it. So let's look at the first step. The first step, you are going to start with N-methyl-aniline, and you react with acetic anhydride, and you form an acetyl group over here. This reaction is an example of a nucleophilic acyl substitution reaction. You should know how to draw this. A nucleophilic acyl substitution reaction, and actually to do this reaction, you just kind of boil these two up, and you will put an acetyl group on here. The byproduct is acetic acid. AC2O is CH3 C double bond O, O C double bond O CH3. Okay? It's an acetyl group joined essentially by an oxygen. The second step is a reaction when you look at a product, is arising from and installing this whole group here at the ortho position over here. This is a, who knows what reaction is this? It's a name reaction. Starts with F. It's a Freedom-Cross acylation reaction, okay, where you are going to use a Lewis acid, okay, and you are going to carry out electrophilic aromatic substitution reaction, and you should be able to not only draw the mechanism, but explain why the reaction occurs at this position. Fantastic, okay? It's going to be able to occur at this position, which is ortho, because this group is electron donating. Okay, it's an ortho para director, but this para position is blocked. The chlorine substituent is an ortho para director, sorry, this and that. But of these two, you know this is going to be a stronger effect for reasons I've just explained to you. So the product you see is this guy over here. The next step is a reaction where you are basically going to remove this group over here, the acetyl group. And you remove this group here using sodium hydroxide in water. And you should be able to draw this because this is also a nucleophilic acyl substitution reaction. You're converting the amide, you're hydrolyzing the amide to basically an amine. So step 3, you should be able to draw as well. Step 4 is you install now this particular group and you add this group here onto that, which is also, this is actually an SN2 type reaction, an SN2 reaction, a substitution reaction onto the carbon bearing the chlorine. Sorry, wrong. This is a nucleophilic acyl substitution reaction which reacts on the acid chloride to give you the amide. The next one is the one which is a SN2 type reaction to give you the corresponding amine. And then you have an intramolecular reaction, which is an intramolecular actually it's an intramolecular addition onto the carbonyl followed by loss to give you basically the amine. All of this you have already done. So the question that I'm going to leave for you is like this. And don't ask me whether they are answers. I'm not giving you answers for that. You're going to have to work this out because I'm going to give you some questions that you can look at later on, which is similar to this. Okay? So my question is like this to you. Okay? Listen carefully. You need to be able to identify each type of reaction that is occurring over here. In other words, here you know it's a nucleophilic acyl, here you know it's a phylloplast or an electrophilic aromatic substitution, here you know it's an SN2, and so on. That's the first question. The second question is to be able to draw the mechanisms for each of the steps. The third question is much subtle than that. Okay? The third question is, you know this synthesis, you put on this group over here, then you take off this group. Why do you do that? In other words, why did you put on a group here only to take it off? Okay? Why can't you just put this particular group on first, okay, and then carry out the reaction? Because anything that you basically add on a step in industry costs money. Remember, you're synthesizing a drug. You want it to be as short as possible. Nevertheless, you put on an acetyl group here, and then you have to remove the acetyl group in a step basically later on. A group that is put on basically for a while and taken off is known as a protecting group. Okay? It's known as a protecting group. And the criteria for protecting groups is like a certain form of birth control, okay? It must be easy to put on and it must be easy to take off, okay? And effectively, and it should be effective during, whatever you're trying to protect, okay? So, in this sense, okay, a protecting group that is used in this case is essentially the acetyl group. So my third question is, why do you have to do that? Why can't you immediately take this guy, put on this group over here, and then you make short the whole synthetic group? Okay? That's my third question. My fourth question is like this. See this step over here? Why does it react at this position and not this position at this point? That's my fourth question. Okay? Yesterday, I scolded my graduate students. I told them, for everything that you do, you need to ask other questions. You cannot just accept that something actually just A gives you B and you don't even care, okay? Because that's not the nature of science. The nature of science is to keep asking questions. So if I gave you this, you need to be able to ask questions. Why is it like this? Why is this the route that it shows? Sometimes I cannot tell you the answer because maybe it's a trade secret. But the questions I just asked you over there, you should actually be able to answer them. This is a very good animation website, so please have a look at them. And then these are the things that we really looked at when we were looking at the lecture material. Okay, that's the end of your mechanism section. And I'm just now going to do a very, very quick revision, okay, which I require to write stuff down, okay, because it's a bit like a checklist. Okay. Before I do that, I'm just going to reiterate certain things. Firstly, the first thing I want you to know is that when you are looking at reaction mechanisms, you need to be able to draw the arrows regardless. Number two, in general, you understand the concepts. Do not memorize anything. And in general, the things that I have written at the thing means that it is for information from the point of view that you shouldn't be memorizing any example. The slides that I wanted you to memorize without understanding anything, I have already highlighted to you. And there was a slide where you look at the reagents in the case of algae, which you are supposed to memorize, right? Okay? So you need to know all of these because in your mind, you need to be very clear, okay? You don't need to memorize the examples like, say, how to make glucose and things like that. It's irrelevant. That is not the point of showing you the slide. Okay? The point of showing you the slide is to demonstrate the chemistry. Okay? So in this case, You don't memorize the synthesis. Do not do that. But if I gave you something similar, you should be able to work out each step of it. That's the difference, okay? Remember that. So, I'm going to talk about what we actually have done during this time. And this, as I said, is going to serve a little bit my projectors. So, what we have done in overall was to also introduce quite a lot of terminology. And so, you need to know the terminology, essentially. For example, we talk about resonate. Do you know what resonate is? Do you know what resolution is? And basically, what is optical notation? And we talked about nucleophiles. And we talked about electrophiles. And then the leading group. And then basicity. These are the concepts and the terminology which I have kind of introduced to you, okay, which are the key ones that I'm bringing out over here. We actually also, maybe somewhere here, I should also put things like epimerization, okay, versus racemization, subtlety in the terminology. So, you must know what these words mean and in what context you will use them and the properties of these. It's like your best friend forever, okay? Your best friend forever, you know exactly their characteristics. They don't like eating in Texas chicken, they love eating Popeye's chicken, whatever it is, you know, okay? And this is basically the relationship that you should have with this sort of terminology here. You need to know it so well that it becomes a language that you're very, very familiar with. Properties of this, definitions of this. And somewhere also here we talked a lot about the concept of inductive effects, which is I, and you can have a minus I, which are relationships which are through sigma bonds, where one is going to be more electronegative than the other, and is sucking electrons away. That's minus I. Plus I are groups that are alkyl groups which donate electrons via a sigma bond. They are usually not very strong effects because they're just through sigma bonds. I mean, if you have a single bond, you can only have the electrons closer to you or basically a little bit further away from you. You can't really do very much more to that, right? So that's inductive effect. And we talked about resonance effects, and that's the R effects. Again, you have plus R, donating via resonance, very strong effect. Minus R effect, withdrawing electrons through resonance, which means through you drawing all these resonance structures. They are very strong effects in general, with the exception of in the case of halogen. And then we have sterics. And you know what? Almost everything in terms of chemistry and also in terms of math chem could be explained using inductive, resonance, or steric. So it seems like there's so much stuff that you would think that you have to learn, but in reality it comes back to the three of these factors, the trifecta. Okay? And then I also introduced to you terminology associated with stereo selectivity, regio selectivity, chemo selectivity, although I don't think I already mentioned this, but I'm going to mention it now. Okay? And stereo selectivity means when it prefers one stereoisomer over another, Regio selectivity means when you got an alkene, you got a carbon-carbon double bond, it reacts at one of those carbon of the double bond over another. Okay? Chemoselectivity means you got two different functional groups, and it's going to prefer to react on one over the other. For example, if you got an iodide, alkyl iodide versus an alkyl bromide within a molecule, it reacts at the iodide preferentially to the bromide, then it is effectively a chemoselective reaction. And related to stereoselectivity is a related concept called stereospecificity. And there's a very slight difference between both of them. If I carry out a reaction and I get 80%, okay, of one stereoisomer versus and 20% of the other, that reaction is stereoselective for one isomer. In an SN2 type reaction, by virtue of the mechanism, you will always get inversion of the stereochemistry if you start from a carbon-carbon. That is a stereospecific reaction. It's stereospecific by nature of the mechanism. It will have to always give you 100%, okay, of one stereoisomer. That is stereospecific. You've only done one stereospecific reaction, which is an SN2 reaction. Everything else is more or less, you know, your preference for an E versus a Z. All of those are actually stereoselective, not stereospecific. This then leads me to also say that when you look at regio selectivity, okay, you also can include things like auto, para, and meta. That is examples of regio selectivity. Okay, that's an example of regio selectivity. And then we talked about all these name reactions. You know, if you were in the olden days, if you invented a reaction, you can name it after yourself. Okay. These days, nobody really encourages that sort of thing. There are committees who decide how to name things. Okay. And the name reactions or the name whatever it is, okay, are things like the Zatsiev. Remember we talked about the Zatsiev rule, the Hoffman rule. This is with regards to the alkenes. And then we've got a good friend, Markovnikov. And then we have the aldol reaction, although this is a name reaction, but it's not after somebody. But the Michael reaction is. Okay. And then you have the Friedel-Crafts acylation and the alkylation reaction. These are name reactions that we have actually done. So when you go through your checklist, make sure you know what this is. Don't look at your checklist before you do the study. Study and then after that review in your mind whether you understood each of these and you know what they are. We also looked at some kind of really important concepts. And the concepts are arrow pushing, resonance, protomerism, nucleophilicity, which I kind of stuffed up, okay, but I fixed it with a different slide, and then I talk about the groups. And I'm just going to mention these two in a bit. Arrow pushing is quite clear. If you draw me an arrow that is basically going in the wrong direction, it's almost an unforgivable sin, in my view. Right? So don't push arrows the wrong way. If you don't know this, you have at least 2 weeks to sort it out. Come and see me. Come and see me, come and see Man Hong. Man Hong was my postdoc, so he will know this stuff like the back of his hand. Okay? So, arrow pushing. Resonance, I already told you there are some sort of guidelines associated with what is in fact resonance. Resonance are not real structures, they are just contributing to a real structure. Tautomerism are real structures. And although I gave you some examples of drawing tautomers, there are more, okay? I cannot just keep drawing, okay? I just wanted to demonstrate to you that these are the tautomeric forms. A lot of the multi-heterocyclic systems have more than the forms that I've drawn, okay? You need to understand that. I'm going to talk about nucleophilicity and leaving groups. And firstly, I'm going to talk about leaving groups because they are usually going to be weak bases, and that is a very important factor that you will need to remember. Nucleophilicity is complex because in general they are good bases, but this rule doesn't always work. And this is where there was this confusion earlier on. Make sure you download the latest slides on that one. Okay? In other words, what I'm saying is that, okay, you have a situation where nucleophilicity, a good nucleophile is a good base, but it is not always the case. And the weirdest thing of all of this is the situation associated with the iodine. Actually, an iodine is a good nucleophile, but it is actually not a good base. Okay? And so, it is also a good leaving group. So you will say to me, how come that is going to work? How is it going to work? That means that it's easy to react, it's easy to come off. Okay? And this means that in a sense, if you think about these sort of reactions, okay, if you react with an iodine, okay, you might be able to get more of a reversible reaction. It can go forward, it can go backwards. Whereas if you react with an OH minus, the OH minus reacts, right? And then it doesn't want to leave. It's effectively a one-directional reaction. Okay? Okay, you guys are okay. Okay? So, in essence, it's not really that difficult to work out, and it's not really that contradictory because it's okay when something is a good nucleophile and something is also a good leaving group. It just means that the reaction is reversible. Okay? So I know you guys are a little bit confused because you think that how can that be? Because in general, this group and that group are independent, orthogonal to each other. But I'm saying that it is not necessarily so. In general, it is orthogonal to each other. Those groups that are good nucleophiles are actually lousy leaving groups. That is true to say, but it's only general because there are exceptions to this rule. This sheet that I've just outlined over here are basically a summary of the sort of terminology, concepts, and main reactions. Okay, it's going to be your checklist. And now I'm going to go through and summarize very, very quickly what we've done. Essentially, you'll be only over pages. Okay? And this is associated with the reaction mechanism. In terms of reaction mechanisms, we talked about 5 main mechanisms, okay? And they're all kind of related to each other in some concept. And I started by talking about substitution reaction. Specifically that on an sp3 carbon. Okay, substitution reaction, where it is RLG reacting with the nucleophile, giving you overall this guy over here. And then I also talked about, related to that, so I'm going to just give you space, I'm going to write this down to make sure. So you have an sp3 going to an sp2 carbon in general. So let's talk about substitution. Under substitution sp3, there are 2 mechanisms that I told you, SN2 and SN1. Actually, after I've done this summary, you probably don't need to go back and look at the notes unless you really don't understand it. Okay? And SN2 is a substitution with bimolecular. It's a concerted reaction, one-step reaction. And the critical thing is that you need to have a good nuclear power. If you don't understand my decision tree, don't worry. That was just meant to help you. If it confuses you, throw it away, okay? You need a good nuclear file. A primary is better than a secondary. A tertiary doesn't react. It is very, very steric sensitive. It is stereo specific. We already discussed this just now. It's a concerted reaction. I mentioned it earlier on. It's one step. And you're going to say to me, what happened to all these other things that I told you? Okay, you know, I tell you something, you want to do substitution reaction, the leaving group for any substitution reaction has to be good. If you don't have a leaving group that is good, nothing is going to happen, right? So don't worry about this when I summarize this, I'm just giving you the key point. Good nucleophile sterics. Good nucleophile sterics, okay? SN2 reaction. No need to obsess about anything else, okay? In an SN1 reaction, we are saying, okay, what is the issue associated with this? You know, the issue is that you don't even have to have a good nucleophile. A lousy nucleophile is okay. Critically, you have a tertiary is better than a secondary. Or you have to be able to have a stable carbocation intermediate. In other words, you are saying in this situation, whenever you have an SN1 type reaction, if you can form a more stable carbocation intermediate, there is a driving force to generate the carbocation, then you will be able to get the carbocation intermediate. So solvents are kind of pretty important here. They are important because of the fact that they can stabilize the carbocation intermediate. It is a two-step reaction, two-step reaction, because you're going to generate the carbocation intermediate, okay, and then that is going to react. And then it is because of the fact you get the carbocation intermediate, a whole bunch of things can happen, including rearrangement, which is not desirable. And when you think about all of these, you need to remember, therefore, that in an SN1 type reaction, you have a carbocation intermediate. The driving force to do this, always you have to have a good leaving group anyway. So what is going to make you decide is how stable you are going to be. And you can be stable because you're tertiary carbocation or you're benzylic carbocation. But sometimes your friends, if they are polar, they will help you because they will say to you, we know you're going to go through this period where you have no money, it's okay. I'm going to come around and bring tapao some food for you so you won't be starving. So you are basically have friends which are going to stabilize your state of poverty, okay? And therefore they are the polar solvent friends. That's why they are important. They are going to be those guys who are going to be your safety net. And they are going to help you decide that you're going to generate a carbocation intermediate. Otherwise, don't even bother reacting. No need to form a carbocation. Okay? You remember, for all of these, there are choices, you don't have to react. That is a choice. Okay? So the question is, what makes you react? Okay? And these are the issues that I've outlined over